We're going to start this section with a review of non-covalent or weak interactions because these are critically important for the function of a lot of biological systems. And so we typically think of chemical processes as the formation and breaking of covalent bonds, but these non-covalent interactions are also really important for different properties of molecules and also in terms of biological systems to allow them to be dynamic. And so the covalent bond, of course, is when electrons are shared. So we can think of, for instance, a carbon-carbon bond in a molecule of ethane as an example of a covalent bond. Now, non-covalent interactions are going to be underneath this blue line. Right. And the first one we can look at is an electrostatic interaction. So the most commonly, one common example, I should say, electrostatic interaction is, for instance, between a sodium cation and a chloride anion, right? All right, so that's basically an electrostatic interaction, which is an interaction between two charged species, right? So in this case, this would be an ionic bond, and we typically think of that for like a salt crystal, but these are slightly different in biological systems, as we'll talk about in a later video. So hydrogen bonding is the next one, and one of the most famous hydrogen bonds, of course, is that between water and itself. So we'll discuss this in more detail. So, for instance, we can think of the hydrogen bond between the hydrogen of one water molecule and the lone pair of a second water molecule. So that's a typical hydrogen bond that we'll see over and over again as we continue through our studies of biochemistry. And then there are van der Waals forces. So this is a combined term to talk about that includes several different types of interactions, including dipole-dipole interactions, induced dipole interactions, and London's forces. And so remember, this final force down here is a reason why, for instance, that the boiling pressures of different different nonpolar molecules increases as you increase the carbon chain. So for instance, ethane, right, which is C2H6, has a boiling point of negative 89 degrees C. Whereas hexane, C6H14, has a boiling point of, 68 degrees C. Okay? So even though these don't have, for instance, lone pairs to form dipolar or hydrogen bonds, the boiling points still increase because of these London's forces. Okay? So again, this includes not only dipole interactions, but also what we might think of as interactions between nonpolar molecules. All right, so what are the energies of these? So we're going to look at the relative energies of all these real quick and compare them to covalent. So covalent is going to have the highest energy. So again, using our example of the CC bond in ethane, this is 377 kilojoules per mole. Okay. Now, we can think of this directly as a bond dissociation energy. So since this is a positive number, what that means is this is the amount of energy it takes to break the CC bond of ethane. Okay. So we can think of these next few energies in the same way. So a typical energy for an electrostatic interaction is 13 to 17 kilojoules per mole in a biological system. Okay. So what that means is that, again, since this is a positive value, it requires 13 to 17 kilojoules per mole in order to break a typical electrostatic interaction. H bonds will be 2 to 21. kilojoules per mole. And then van der Waals are the weakest at 0.4 to 0.8 kilojoules per mole. Okay. So there, as you can see, for the covalent interaction versus these non-covalent interactions, this is over an order of magnitude larger for the covalent interaction than any of the electrostatic interactions. So covalent interactions are by far much stronger, but these weak interactions are really important because one, there are multiple. When combined, for instance, if there are several electrostatic interactions, that really increases the overall, for instance, stability of the system. And then second, even in bulk, even if there are, for instance, 10 electrostatic interactions for instance, a combined stabilizing energy of 170 kilojoules per mole, each individual interaction can break very easily because of the low energy. So one way to illustrate this is to look at, for instance, the relative energies on this energy table shown in the slide here. Okay, so for instance, a covalent bond is going to have 377 kilojoules per mole, so that's going to be around between 10 to the second and 10 to the third on the figure here. So this, the y-axis is an energy, and so this is an increasing energy. 10 to the second is 100, 10 to the third is 1,000, so a typical covalent energy of a covalent bond is going to be about between 10 to the second and 10 to the third. So we'll say 377. All right, so that's also denoted in this blue text here that shows the region for covalent bonds and biomolecules. Okay, so importantly here, down in red are non-covalent interactions. So salt bridges and hydrogen bonds are around 10 kilojoules per mole, and then van der Waals interactions are less than 1 kilojoule per mole. Thermal motion lies in between these two, so that means the energy coming from the surrounding environment, so because of the temperature of the environment, right, that surrounds the temperature in these biological systems, is somewhere in between. So what that means is that these can constantly be broken because there's enough energy to break these interactions, the electrostatic interactions, the H bonds, and also the van der Waals. And so what that allows for is for biomolecules to be very dynamic. So that means they can move, they can respond to environmental changes very easily because individual bonds can be broken. And so they kind of have sort of a breathing type of motion you can think of. And so this is useful because you can also think of this in terms of, let's say, we couldn't overcome the ability to, let's say we were covalently bonded to the floor, for instance, right? That means we couldn't walk, we couldn't respond quite as easily to external stimuli than we would be normally, since we can walk around and move around towards or away from different stimuli. So in the same way, biomolecules are very similar. And so we're going to talk more about these intermolecular or these weak interactions, these non-covalent interactions in the coming up videos.